Hi, I'm Dr. J, and this is a video about regression, and in particular, regression using categorical explanatory variables. In a previous video, hopefully linked right up here, we discussed categorical explanatory variables that only had two levels, and we noted how we could turn that into a simple linear regression model. In this video, we'll talk about categorical explanatory variables that have more than two levels and how you end up with a multiple regression model. As usual, down below, there's a PDF version of these slides. Otherwise, we'll just jump into it. In that previous video, we used a subset of this example. Here in this example, again from the Statistical Sleuth, the Sleuth 3R package. Love it. There's this example where we have 6 different groups of mice. The groupings are done by different diets that the mice were on. So on the x-axis there, we have 6 different diets that these mice were given. On the y-axis, we have the lifetime for that mouse. The variability you see on the x-axis is just due to jittering the points, so it's nothing real, right? All we have are 6 different groups of observations here that hopefully you can see are distinguished by a slight gap between them. And so now we're trying to figure out how we can write this model or model these data using a regression model. The way that we're going to do it, here's sort of the 3-step process to do it. Step number 1 is you need to decide what level of the categorical explanatory variable to use as your reference level. Good choices are typically controls or placebos or the group that is sort of the standard. That's typically the group that you want to use for your reference level. In this case, in this experiment, this N85 was in fact that reference level. Step 2. In step 2, we're going to construct a bunch of dummy variables using these indicator functions, which I explained in the last video. As a reminder, this indicator function is just 1 when the statement within the parentheses is true, and it's 0 otherwise. And we're going to construct these dummy variables using this indicator function for every level of the categorical explanatory variable that's not the reference level. So in this example, we had 6 different levels. If we take one of those as the reference level, we have to construct 5 dummy variables. So here they are. The first one for the NR40 diet, the second one for the NR50 diet, the third one for the NP, fourth RR50, and finally low pro. And now you'll see that in the notation that we use, instead of just having one xi, we have an xi1, and an xi2, and an xi3. So for every observation, we are going to have to introduce 5 new dummy variables to model this categorical explanatory variable that has 6 different levels. So it's always going to be the number of levels minus 1. All right, and then what we're going to do is that we're going to run what's called a multiple regression model using these dummy variables. Now, if you're following along in this playlist, this is the first time we're going to have talked about the multiple regression model, and I hope that the relationship between this and the simple linear regression model, when we have a binary explanatory variable, makes that transition from simple linear regression models to multiple regression models hopefully pretty seamless. We'll see. All right, so this is what the multiple regression model looks like. So instead of having just a beta naught plus beta 1 times xi, now we have a beta 1 times xi1 plus a beta 2 times xi2 plus a beta 3 times xi3 plus a beta 4 times xi4 plus finally beta 5 times xi5. And again, the number of betas that you have here will depend on the number of levels of your underlying explanatory variable. In this case, since we had 6, we had to add on 5 dummy variables, and we have a beta associated with each of those, and we end up with a total of 6 beta parameters if we include that intercept. All right, so just as an understanding of how to interpret these parameters in this model, the first one is to think about what happens when all of those x's are 0. When all those x's are 0, the only way that occurs is if we're at the reference level. In this example, we have the diet is N85. So when the diet is N85, then beta naught is the expected lifetime for the mice on that diet. Now, like before, we can think about situations when the x's are 1, but under the way that we constructed the x's, only one of them can be 1 at any given time. And so if we imagine that xi1 is 1, then that only occurs when the diet is nr40. If you go back to the previous page, you will see that that only occurs under nr40. So therefore, beta naught plus beta 1 is the expected lifetime for that group that is on that diet. We get a similar result for xi2. That's the expected lifetime at nr50 is beta naught plus beta 2. Beta naught plus beta 3 is the expected lifetime for the NP group. Beta 0 plus beta, beta naught plus beta 4 is the expected lifetime for the RR50 group. And finally, beta naught plus beta 5 is the expected lifetime for the low pro group. Now, hopefully it's obvious then what these other betas are. So beta 1, beta 2, beta 3, 4, and 5. Right? Those betas are simply the expected difference in lifetimes between one of those diets and the reference diet. Right? So if it's beta 1, that's the expected difference in lifetime between NR40 and NN85. Right? So beta naught is the lifetime under the reference group, and then all the other betas are differences between that reference group and a particular diet. Alright, so here's how we code it up. And again, for those who know R, and regression for that matter, there's going to be a much simpler way to do this. So this is really for illustrative purposes. So we can construct our dummy variables up here. We then run the regression. You see we just put in all the dummy variables, x1, x2, 3, 4, and 5. We can take a look at the output in terms of the point estimates. We can take a look at the credible intervals using the conf_int function. We can look at the summary analysis, and now you'll see here that there are a number of additional lines, one for each of the new dummy variables that we created. Alright, so just to remind you about interpretation, when we have categorical explanatory variables and we do this dummy variable encoding, then beta naught is just the expected response when we have the reference level of the explanatory variable. Right? And the way that you see that is that the only way all of the x's are 0 is if you're at that reference level. All of the other betas are expected changes in the response when you move from that reference level to one of the other levels. Right? And the way that you can see that is if you start with all the x's being 0 and one of them goes to 1, then really what you've done is you've changed the diet from the reference diet to one of the other diets. Right? Or if you have a non-diet example, right, then use it in that example. All right, as an example, if you go back to the previous slides, you will see that we have these numbers, so we can just pull them out. So here's an interpretation for that intercept beta naught. The expected lifetime of the dice on the NN85 diet is 32.7. Oh, I need to update this. It's actually in months, not weeks. And there's a 95% credible interval ranging from 31 to 34.4. The expected increase in lifetime for mice on the NR40 diet compared to the NN85 diet is an additional 12.4 months with a 95% credible interval of 10 to 14.9 weeks. Finally, we can interpret that R squared. The interpretation of R squared is the proportion of the response variability, in this case lifetime, that's explained by the model. So 45% of that variability is explained by this particular model. All right, as a picture, this is what's going on. So in the binary categorical variable video, we only had 2 groups. Now we have 6 groups. One of those groups is the reference group. On this picture, it's the one on the far left, that NN85, and beta naught is just the mean lifetime for that group. So it's represented by that dashed line running right through the middle of this picture. That's the beta naught. All of the other betas are then deviations from that line. So we have beta 1, which is the difference between the NN85 group and the NR40 group in terms of the vertical distance from the mean lifetime of the NN85 diet to the NR40 diet. And you can do that for the other betas as well. Now, we had a video previously, hopefully linked to up here, where we talked about a multiple group model. So we had this scenario where we had different groups indicated by J. We had observations within the group indexed by I. We had all the groups were independent, normally distributed, but each group has a different mean, mu J, and then a constant variance from there. And now we can reparameterize that model into our regression model just by noting that the mean lifetime for the different groups from mu naught up to mu 5 are associated with beta naught, and then beta naught plus beta 1 or beta naught plus beta 2, or always beta naught plus another beta, the one that's associated with the dummy variable for that particular diet. All right, as a summary of how you deal with categorical explanatory variables within a regression context is that number one, you have to choose one of the levels of that categorical variable to be what's called a reference level. Then you're going to construct dummy variables through indicator functions for all of the other levels. So any of the non-reference levels you're going to construct a dummy variable for. Then finally, you just throw that into a multiple regression model and you have this pretty convenient interpretation in terms of deviations in the response between the reference level and all of the other levels. All right, the next video in this series is going to talk about the multiple regression model in more generality and also in more detail. So this is going to be one specific example, but there are going to be many other examples of ways to construct a multiple regression model. I hope to catch you there.